This subVI accepts two bit streams, evaluates the two bit streams or compares them to see how many bit errors or bit differences exist between the two arrays, and then reports that as the bit error rate, or BER. All these bit stream inputs A and B. As you can see, the alignment there was probably not crucial since I started moving stuff around already. What I'm doing here is something that you would not necessarily need to do, but I'm just trying to illustrate some specific values for our two different bit streams, just so we can talk about some of the issues here. I'll set as one difference there at the second element in the array. Probably the most common way of establishing which elements are different is to use the exclusive OR operation. And that says that if there's any mismatch between the two Boolean values, you generate a true, otherwise you generate a false. So you can see we've generated a new error where the bits that are different is highlighted with a true output. For this purpose, you could also make good use of the not equals or not equal to comparison. Really, either one of those techniques would work fine. All right. Now, this is a handy little construct that allows you to accept an array, and then it simply adds up the array elements. Now, adding trues and falses together doesn't make a lot of mathematical sense, I guess. So what we can do is convert the Boolean into either a 0 or 1. So 0 for false, 1 for true. So now we've got something that we can actually add up. So when we run this, we see that the sum is 1. Let me introduce one more difference and try running that again. Sum is 2. So this allows us to count up all the number of times that we have a discrepancy between those two bit streams. Now I'll point out that here the data type is integer 16, which is a little bit limiting. Turns out that the maximum value on this is on the order of about 32,000. If you're trying to deal with really long bit streams, and you potentially have lots of errors, then that value might end up being too small. Now, if we change the data type to something that's an integer but longer, in this case the I32, and there's even longer integer data types if that's not satisfactory. But the advantage here is that we can actually count up many more number of bit errors than what we could do otherwise, because that summing node takes its cue from the data type coming in, and so that can potentially cause some limitations for you there. All right, so at this point we've got the counting concept figured out. Other things we need to do is deal with the potential that the bit streams are not the same size. Normally you wouldn't do that by design, but if they are different sizes, then you definitely need to know about that. Probably signals some kind of error in your other surrounding code someplace. So the array size should be applied to both bit stream inputs, and we can use the not equal to as our mechanism for comparing those. Of course, the output of the not equal to, that can get sent directly out as our array sizes not the same output. But another thing we need to be able to do is switch the bit error rate, or the BER value, between a valid calculation and a result that indicates the so-called not a number, or NaN. So what I'm illustrating here is that we use this select node to pick between not a number if we see that the bit streams are not the same, or we generate the calculation that says tally up the total number of errors, divide by the array length, and that gives us our bit error value.